Greetings, Panthers. It's Dr. Augustine again. Hope you're doing well. We're going to talk about a couple of terms in this video. Again, Chapter 2, there's a lot of definitions that we need to get at so we can start doing some real chemistry. So one of the things we want to talk about are how protons impact what an element is, and that won't take too long. Then we're also going to talk about isotopes. We are going to talk about mass spectrometry. And we're going to talk about how to calculate the number of protons, neutrons, and electrons from what's called atomic symbol notation. Okay, so let's start with the first thing. You're all familiar with this sort of description. If you've seen a periodic table anywhere, it often looks like this. There's usually a big letter. That's the atomic symbol. Many times on the periodic table it'll have the name of the element. Sometimes it does not, but it'll just have the symbol. There's usually a big number on it, and then there's usually some other numbers. The big number is an integer, and the sometimes smaller number, sometimes same size number, usually is a decimal with a bunch of numbers after it. In fact, always is a decimal with some numbers after it. So let's talk about this big number first, and let's talk about what that means. So this big number right here is called the atomic number. And obviously in the case of carbon, that atomic number is 6. So what does that 6 actually represent? Well, the 6, what it represents is the number of protons in carbon. And this is a really key idea. The big number on the periodic table tells you the number of protons in that element. In each one of those atoms, there's 6 protons. And the 6 protons is what defines that element to have the properties that it does. So if we were to get on a spaceship somewhere and fly to another planet, and let's pretend there were some creatures on there that spoke a different language. It's probably not going to speak English on another planet, but they would have, undoubtedly or highly likely, they would have carbon on their planet. And if we did measurement of this element and we found carbon, the way we would tell it was carbon is if it had 6 protons. Okay, so the protons, that unique signature, makes an element an element. So you can think of it this way: that big number, if you know that number, you already know the element. Even if you don't know it offhand, if you know that number, you can just look it up and you can say, oh, that's carbon, that's silicon, that's hydrogen, or whatever. Okay, so that's an important key piece. Now, within each atom, it is possible that you can have other forms of that with different numbers of neutrons. So the 6 doesn't tell us anything about the number of neutrons, it just tells us about the number of protons. So in fact, carbon has a couple of different forms. Carbon has a form with 14 mass, 13 mass, and 12 mass. These are the 3 different primary forms of carbon. Now, what do I mean by 14 mass, 13 mass, and 12 mass? What I mean is, if we take this mass and measure it relative to other things, we find out that carbon actually doesn't weigh 6, it weighs 12, 13, or 14. So where's the 12, 13, or 14 coming from? Well, if you remember from an earlier discussion, we had that protons and neutrons are basically the same mass. Okay, neutrons weigh slightly more, but they're basically the same mass. So if the mass is 12, and I know that there's 6 protons, that tells me that there must be 6 neutrons as well. And the total mass is the sum of those two things. Now you might be asking yourself, well, why don't the electrons count? Okay, so let's just finish this out. This is 7 neutrons, and this is 8 neutrons. But a good question would be, okay, well, yes, I understand that if I add up 6 neutrons plus 6 protons, I'm going to end up with some mass around 12. If I do 7, I'm going to get something around 13. If I get 8, I'm going to get something around 14. But you might be saying, what about the electrons? I know carbon has some electrons, and why doesn't that have a mass? Well, if you remember the relative masses of the electrons, the mass of an electron is about 1,800 times lighter than a proton. Okay? The electron, so I should say electron, is about 1,800 times lighter than a proton. So what is that analogy? Let me give you an analogy of that. A lightweight sports car, let's say something like a Mazda Miata, probably weighs about 2,000 pounds, might weigh a little bit more than 2,000 pounds. If I took a can of beans or a can of peas or something that I bought from the store, those typically weigh about 1 pound. So if I was considering the mass of my Mazda Miata and I put a can of peas in the front seat, would you say that the mass had changed very much? Probably not, right? That 2,000 pound object now weighs 2,001 pounds with the mass of the peas in it. So that's what this is about 2,000 times lighter than a proton. So the reason why we don't consider the electrons is they don't really weigh that much, certainly not compared to the neutrons and protons. So the mass is primarily in the nucleus, not in the electrons. Okay, so we have a notation system that's used, and it looks something like this. So we have 3 elements on the notation, and we're going to introduce one more element, and if you have all 4 elements, you can tell anything you want about an atom. So the big X is the atomic symbol. All right, in this case, X would be carbon, X would be C. So we have, let's just write the notation for carbon. All right, and this is for any element on the periodic table. So we can put that letter in for whatever the atomic symbol is. Then Z is called the atomic number. And A is called the mass number. All right, so we already said what atomic number is a few minutes ago. Atomic number is the big number right here, right? So in carbon, if we know the element's carbon, we can just put that 6 down as a subscript. And then the mass number is equal to the sum of the protons, 6, plus neutrons, in this case 8, in this case 6. So I can write, if I'm referring to the specific type of carbon that has a mass number of 12, I can write the notation this way. 12 in the superscript, 6 in the subscript, and C. And this tells me I have a specific type of carbon. We call these specific types isotopes. Okay, and I already mentioned carbon has 3 unique isotopes. So we have 13 carbon, and we also have 14 carbon. And there's different amounts of these in nature. These are called the relative abundances. We'll come back to this in a little while. So nature has certain percentages of these. But these 3 different forms of carbon can be found in nature. Carbon-12 is by far the most common type, and then there's these other ones. And you notice I've already used the word. We would call this carbon-12, sometimes written as a dash, carbon-12, carbon-13, and carbon-14. The reason why I don't need to say anything about the 6, I only need the 12, 13, and 14, is because the fact I'm telling you it's carbon means it's 6. I don't need to figure out what 6 is. Once I tell you that it's carbon, you know that it's 6, or vice versa. If I tell you some element has an atomic number of 6, you know that it's carbon. So our notation is either this, the element symbol, or we could say carbon-12. Those are both saying the exact same thing. Those are equivalent statements to one another. And depending on the context will depend on how it's written. So you might be asking yourself, well, how did they figure this out? I mean, how do they know that there's a certain amount of carbon and that they have 12, you know, it has 6 neutrons and 6 protons? Like that sounds like a pretty interesting or amazing thing. How did they figure that out? And the way they figured that out is a technique called mass spectrometry. So mass spectrometry is an instrument in which you introduce a sample into the mass spectrometer. The sample can really be anything. Now there's details, you know, certain mass, if it's too heavy, it doesn't work well, or only certain times the mass spectrometers work well with certain masses. But if you, let's say we just kind of introduce a normal type sample with carbons and oxygens and hydrogens or whatever. If I introduce that into this chamber, and this is we pumped under a vacuum, there's some way of breaking electrons off of my sample or adding electrons. And you remember what that's called? That's ionizing it, right? So it's taking a sample that has, that are in their atomic form, and then we ionize them. We charge those particles. Then we send them through an electric field. And if you remember, if you put something through an electric field, a charged particle, it will turn or move in response to that electric field. So some magnets are placed further downstream, and then what happens is the lightest particles get deflected the most. The heavier and heavier the particles are, the less they get deflected by that magnet. If you want to watch a nice analogy of this, there's a nice YouTube video that has an analogy of how a mass spectrometer works using a ping pong ball, a golf ball, and this is a British guy, a snooker ball, which we would call a billiard ball. And the analogy is those three balls roll down a ramp, all of them, because of gravity, roll down the ramp. Then at the magnet part is like a hairdryer, and the hairdryer is blowing at a constant speed, and the ping pong ball will get blown the most because it's the lightest, and the snooker ball or the billiard ball will get blown the least. And then you can separate out particles by their mass to charge ratio. And so what happens is carbon-14 will get deflected the least, carbon-12 will get deflected the most, and we will get peaks corresponding to the relative abundances. So if I have 99% carbon-12 and 1% carbon-13, or let's say 98, 1, and then 1, I'm going to get a big, huge peak for carbon-12. And by the way, this is pretty close to the actual ratio. I'm going to get a big, huge peak for carbon-12. I'm going to get a little peak for carbon-13 and a little peak for carbon-14. And we can do some calculations and figure out exactly what that mass is. So, quick recap then. We have talked about isotopes. That's just a different number of neutrons. We've talked about mass spectrometry. We've talked about atomic symbol notation. We've talked about relative abundances. One more thing, I mean, we've already talked about this, but let's just clarify and finalize. How do we calculate the number of protons, neutrons, and electrons? So let's pretend we have a symbol notation, and let's say we have something like uranium, which is a radioactive material. And let's suppose I gave you this notation right here. Here's one form of uranium, uranium-235. Here's another form of uranium, 238. So, number of protons, that's easy. Number of protons is just that mass number. Okay, so the number of protons is going to equal to 92. Number of electrons, we're going to find out a little more about this in the next video, but there's one more piece of information that we can have, and that goes up here in the top right corner. And that is if we have a charged atom, also known as an ion. If we have a charged ion, we're going to put that charge here. If you do not see any notation in the top corner like this carbon, what that means is it's a neutral atom. It doesn't have a charge. So from this notation, we would say it also has 92 electrons. Because there's no notation, no symbol here, that means that the number of electrons is equal to the number of protons, therefore the charge is the same. And the way we find the number of neutrons that is equal to the mass number, in other words, A, minus the atomic number, Z. So this first one would be 235 minus 92, which is equal to 143. So this one has 143 neutrons, and the other one is 238 minus 92, which is 146 neutrons. All right, so using this type of notation that we have here, we can find protons, electrons, and neutrons from these electron symbols. All right, so to complete this discussion, let's take an element like sodium. If we look on the periodic table at sodium, we would find that its atomic number is 11, and let's say that 23 is the mass number. Okay, so how many neutrons do we have then? So number of neutrons then is equal to 23 minus 11, which is going to be equal to 12 neutrons. So my summary then, protons are equal to 11, electrons are equal to 11, and neutrons are equal to 12. If sodium forms an ion, which it does, it's very commonly Na+. So remember, that's called a cation. Cats are good, so they're plus, they're positive. So since that's a positive ion, what we can do is we can write a plus symbol next to this. So now with this notation, I can now figure out protons, neutrons, and electrons in a situation where I have an ion. So this is no longer 11, but let's think about this for a second. This is 11 protons, and I have a positive charge. Therefore, that tells me I need one more electron in order to be neutral. So there must only be 10 electrons in a sodium plus ion. All right, so using this symbol notation, including ions, we can also figure out the number of electrons. Let me give you one more example of this. Let's take something like oxygen. So oxygen, let's say 2 minus, which is the normal form of an oxygen ion. So oxygen 2 minus, if we want to fill out the rest of this, we need to know a little bit more, but let's say this is 16 and this is 8. So my protons are going to equal to 8. My electrons are going to be equal to 8 with 2 extras, so it's actually 10. And my neutrons are going to be equal to 8 also. It's going to be 16 minus 8, which is equal to 8. All right, so this notation then will give me a complete description of an atom. I know the atomic number, I know the mass number, and I know the charge. With those 3 pieces of information, I can figure out for any element, number of protons, number of electrons, number of neutrons.